introduce Mitchell Khoo, our speaker today. He started his PhD around 2 years ago now, 2 years and 2 months, I think. And he's going to talk about a part of some of the problems that he considered for the first 2 years, particularly solving bottleneck assignments in a distributed way, and then discovering certain structures that comes out of these sort of bottleneck assignments as he's been looking into them. Thanks, Mitchell.
Okay. Yeah, thanks, Aman. So yeah, the title is Solving the Bottleneck Assignment Problem with Distributed Agents. But as Aman mentioned, as I was putting together these slides, in fact, the focus shifted sort of away from the distributed agents part. We'll still see that towards the later end of the talk, but the front end of the talk will be mostly to do with the bottleneck assignment problem itself. Okay, so there are two papers that the material of today's talk comes from. What did I just do there? And that's, yeah, these two papers here. The second one I'll be presenting at IFAC in July. I think that's all virtual as well now. Yep, so let's get started with today's talk. The bottleneck assignment problem is a type of task assignment. And the task assignment problem really arises when we want to have a set of agents and a set of tasks, and we want to assign the tasks to the agents, where in this sense, we're talking about agents quite broadly. We mean agents can be anything from computer processors to robotic arms or taxis or autonomous agents. And tasks can be anything from moving boxes from factories or moving them off pallets or picking up passengers in a city. So anything really in a broad sense. And we want to make a decision on which agent should carry out which task, right? So as you can imagine, there are many applications for these kinds of problems. And this is just reiterating what I said on the previous slide. We have a set of tasks and we want to allocate them to a set of agents. And some applications might be ride sharing, timetabling, or worker scheduling. I've got over here a little drawing of a ride sharing application where we've got 3 cars and 3 passengers that we want to pick up, and we want to make a decision. How do we want, which car needs to go pick up which passenger? So that's just an example of a task assignment problem. Specifically, we're going to talk about the bottleneck assignment problem, and I'll abbreviate that to BAP. So the BAP is a type of assignment problem, and the objective is to minimize the costliest allocation. So the BAP really appears a lot in time-critical problems. So for example, if we go back to our car passenger problem, if we have 2 cars going to pick up 2 passengers, and I've written here the costs that, or the time that it would take for this car to pick up this passenger, and this car to pick up these 2 passengers. If we were to make an assignment according to the bottleneck assignment problem, we would make this solid line assignment, because the largest or the costliest assignment for us, the costliest allocation for us in this case would be 5. On the other hand, if we were to try and assign diagonally across with the dotted lines, the costliest assignment would be 6 seconds. Oops. And so it would not be optimal according to the bottleneck assignment problem. When would we ever want to do this dotted line assignment? Well, if we were to look at different kinds of assignment problems, one other common assignment problem would be the linear sum assignment problem. And as its name suggests, the LSAP involves summing the costs of the assignment. So this sums up to 9, and 5 and 5 sums up to 10. And so in the linear sum assignment problem case, we would then want to make this other type of assignment. Right. But yeah, today we're focusing on just the BAP. The final slide in my introductory.
But when there's one final stage of scope of liability, which we haven't looked at yet. But I hope that Hyper is sort of clear. Asking you questions.
Hello, sorry. That was a bit fuzzy, sorry. Could you repeat that? Hello?
Excuse me, maybe we can leave the questions or type the questions. Mitchell, just continue.
Yeah, all right, I'll keep going. So yeah, there's one more slide in my introductory section here, and it is to do with centralized versus distributed decision making. So a centralized algorithm you'd need all information from all the agents to be aggregated by a single decision maker. And this would mean that there would be a single point of failure, information is not private, and agents must maintain communication with this centralized decision maker. So obviously this is something that we want to try and avoid. And so for our distributed agents, so this will only appear towards the later end of today's talk, but the assumption that we're going to make for our distributed agents is that we only assume that agents have access to the costs for it to carry out each task, and the entire set of costs is unknown to any single agent. So what I mean by that is this red car will only have information, the red information, and this blue car will only have this blue information, and none of these single agents will have the entire set of information, right? Okay, so that was the introductory slides, and the rest of the talk will be as follows. I am going to go through the bottleneck assignment problem formulation. Then we'll talk about an assignment that solves the bottleneck assignment problem. An algorithm that solves the BAP. And the claim here isn't that this is the only algorithm that will solve the BAP, but this particular algorithm that I'm going to go through has some interesting things that we can get out of it. And that is this warm starting of the algorithm. It allows us to take advantage of certain properties to warm start. It also allows us to come up with a distributed implementation. Yeah, so we'll be able to come up with a distributed implementation of this algorithm. In between the third point and the fifth point, I've put in a detour over here. Because it's not really related to the algorithm and it's more a structural, it's got more to do with the structure of the BAP in general. I was going to really exclude it from today's talk, but I'll have a one slide detour to just mention several other BAP structures that are interesting. Right. And then we'll cap it off with a numerical analysis at the end. Cool. So the BAP formulation, in order to formulate the BAP, we need to define something called a maximum cardinality matching, which is abbreviated to MCM. So a matching, just a matching, is a set of edges that are such that no two edges in that set is incident to the same vertex. So if I draw these three edges, none of them can be joined to the same vertex. And as long as they satisfy that property, we can call them a matching. A maximum cardinality matching is a matching of maximum cardinality. So a matching could just be a set of one or a set of two. In this case, with 3 agents and 3 tasks, our MCMs will have size 3. So I'll need 3 to make it an MCM. And as you can note, none of these edges that I've highlighted it contains a common vertex. So if I were to try and draw up a set of all these MCMs, it's quite easy because it's a small problem, 3 agents and 3 tasks. I can quickly scroll through all these different MCMs of this particular graph. And if you'll notice in blue, I've highlighted the largest cost of an edge in this MCM. So 23 is larger than 11 and 2. If I scroll to the next MCM, 19 is larger than 7 and 2, and so on. So in all these MCMs, we can highlight one particular edge that will have the largest cost. Now, the BAP is formulated as follows. It is the MCM that minimizes the maximum weight in the MCM. So it is the particular MCM that has the smallest highlighted in blue weight, right? So in this case, if I were to check all possible permutations, all possible MCMs, 23 is the largest, 19 is the largest, 23. The largest, the smallest blue cost is 17 because it's smaller than 23 and 19. And so this MCM would be a solution to the bottleneck assignment problem. If you'll notice also, because we only care about this largest weight in the MCM, the solution to the BAP is not necessarily unique. There may be two MCMs that both are optimal according to the BAP because their smaller edges are both smaller than 17. Cool, so that is the BAP. Before going into the algorithm that solves the BAP that I was talking about, I'm going to introduce these two definitions. And there's a fair bit of information on this slide, so I'll try and go through slowly. The first definition is of a pruned edge set, and it's defined as follows. So given a bipartite graph G and an MCM M, we define the pruned edge set as the union of M and the set of all edges with weights strictly smaller than the largest edge in M. So I'll try and explain that with the help of this visual aid down here. If I have all my edges in this set E of my graph, all my edges here arranged from smallest edge on the left to largest edge on the right, so in ascending order, the pruned edge set is everything to the left of this dashed black line because it's the pruned edge set is the union of M, which I've circled here. So this is a 4-agent, 4-task case. So the MCMs all have size 4. So I've circled 4 edges in my MCM. It's the union of these 4 edges with all the edges having weights strictly smaller than E11, which is in blue, right? And so all the edges to the left over here are in the pruned edge set. And what's useful about this is it helps us define the next thing, which is the critical bottleneck edge. So an edge EC, I'll say, is a critical bottleneck edge of G relative to the MCM if the edge EC is the largest edge in the MCM and the set of the pruned edge set subtracted EC does not contain another MCM. So again, I'll go to the visual aid to try and help me explain this. So I have my pruned edge set here, and I remove one edge. So I move this dashed line to the left by 1. I remove EC, which is in blue, E11. And then I try and find 4 circled edges within the remaining set. If I can't do that, then I know that my blue edge must be a critical bottleneck edge because remember the pruned edge said to everything to the left is smaller than everything to the right. So this really defines a critical point in our algorithm where if we can find this E11, the moment we try to remove it, our algorithm will terminate and we know that we've reached a point where we found a solution to the bottleneck assignment problem. Now the only remaining thing on this slide is this statement over here that says the set does not contain another MCM. So if I move my dashed line to the right, this set over here does not contain an MCM. Well, this statement here is not that straightforward to do. What we want to instead do is replace this statement with an equivalent statement saying, instead of trying to search for an MCM within this set, we want to instead search for an augmenting path relative to these 3 remaining circled edges. And I'll explain on the next slide why this thing called an augmenting path allows us to replace this statement. Okay, so an augmenting path is a path that must begin at a free task and must end at a free agent and must alternate between edges in the matching and not in the matching. So if I start off with my MCM over here, it's got 3 edges in my 3 agent 3 task case. So I won't be able to find an augmenting path over here, but if I were to remove this edge over here, I now have a matching that's not an MCM because it's not a maximum cardinality matching, but it is still a matching, right? And an augmenting path relative to this matching is a path that begins at a free task, ends at a free agent, and a free agent and free task just means it's not connected to a highlighted edge. It's not part of a matching. And it must alternate between edges in the matching and not in the matching. So there's quite clearly one over here. You can see this path over here is an augmenting path. And the reason why we're interested in this thing called an augmenting path is because if you notice this blue, red, blue path, if I flip the blue and red edges, I start with 2 red edges, and I want to try and recover my MCM, which has to have a size of 3. So if I flip the blue and red edges, I will always be able to regain this MCM, which has size 3. So I start off with a matching of size n, or n-1, sorry, and I'll always be able to, once I find an augmenting path, I'll always be able to recover a size n MCM. And so because of the way we are going to do, because of the way the algorithm works, this condition of searching for an augmenting path is necessary and sufficient for the existence of an MCM. Right, and I'll go into a bit more detail now of the algorithm, and hopefully things become clearer. So the algorithm will have 2 steps in it. The first step is I need to identify my pruned edge set, which involves really identifying the largest edge in the matching. And then after I've done that, I want to prune the set and then find within that pruned edge set whether or not an MCM still exists. So I'll go through this with the help of these 2 visual aids. One is a complete bipartite graph. So there's an edge between every agent and every task and every agent. And I've highlighted an arbitrary matching, an arbitrary MCM in this case. Just go across. Doesn't really matter which one we choose. We can just choose crosses if we wanted to, as long as we start with an arbitrary one. Now, at the bottom here is the same visual aid we had before. It's the set of edges arranged. So it's all of these edges arranged from smallest edge to largest edge. And this edge, as you can see, is 48, has a weight of 48. So it's all the way to the right and so on. Okay, so we start off with our first step. We want to find our pruned edge set. So we know, again, it all revolves around this largest edge in our matching. So E44 is our largest edge. We identify it, and then we come up with our pruned edge set. In this case, nothing's been pruned away yet because, well, E44 just happens to be, we're unlucky, it just happens to be the largest edge. That's fine, so we remove it. And now what we're going to do is we want to search for an MCM within the remaining edges to the left, which remember is equivalent to saying we want to search for an augmenting path within the edges here, relative to these 3 remaining matched edges. As it turns out, we're still able to do that in this graph. So that's all golden. So the next thing we want to do is, again, find the next pruned edge set, which involves this E11 edge now. So we prune everything else, and we come up with this pruned edge set. And then we go to the next step in blue. We want to search for an MCM, or equivalently, we want to search for an augmenting path. So we remove that edge and see if we can still, from this n-1 matching, come up with an n size matching of size 4 in this case. And we're still able to do that, so we're still good. So again, we prune all the way up to here, E21, remove the largest edge, and try and check again for our condition blue. In this case, you can see on our graph that we've lost our edge from B1 and it's completely disconnected from the rest of the graph. So we know that it's not actually possible anymore. So on this small example, it's quite easy to see that we have ended up with this MCM, which is a solution to our bottleneck assignment problem, because remember, we arranged our edges from left to right in ascending order. So all these edges here are smaller than all these edges to the right. And so these 4 edges must be a solution to our bottleneck assignment problem. Okay, so yeah, so that's how the algorithm works. Now I'm going to talk about some things that we can do with this algorithm. The first one is we are able to warm start the algorithm. And what I mean by that is, if I were to have 2 separate BAPs, if I were to have a blue problem and then a red problem, and I were to solve this blue problem according to the BAP and come up with a solution to the BAP for the blue problem, and then do the same for the red problem, solve the BAP, and come up with a solution to this red problem. Now, if I wanted to take the whole problem into account, if I wanted to consider the BAP for the whole problem, for the combined problem, what information can I use? Because I know I have the solutions to these 2 smaller BAPs. What information can I use from that in order to solve this larger problem without throwing away this useful information? The idea is we can warm start the algorithm, because hopefully you recall me saying to initialize the algorithm, we don't need anything aside from an initial MCM. So it can be an arbitrary MCM, the one that I chose at the start when I was demonstrating the algorithm happened to be going across from each other. So E44, E11, and so E22 and E33. But if we were to take advantage of the solutions that we have, so the blue problem has this solution over here, and the red problem has this solution over here. If we were to just combine these 4 edges together, they actually form an MCM of the combined problem. And so since we only need an arbitrary MCM to kickstart our algorithm, we can use this since we know that we've already removed certain edges in the process of solving the blue and red problem. And so we end up with this MCM. On the other hand, if we didn't have access to that information and we just did it blindly, and we chose an arbitrary MCM to start with, we might not be so lucky, and we might end up choosing this particular MCM that involved having to prune edges away before we arrive at a solution. Okay, cool. So that's something neat that we can do with the algorithm. And now I mentioned that we're going to take a detour, and we're going to talk a bit about the structure of the BAP in general. And why I'm putting it at this stage of the talk is because it sort of relates to the idea where we're combining 2 BAPs, 2 separate BAPs, and finding the solution to the combined problem. And so the idea is these 2 points here. The first one is, what does it mean for 2 BAPs to be separate? So if I go back to my example of 2 cars and 2 of my cars and my passengers, if I had two sets of problems in two different cities, for example, that were really far apart, I know I can intuitively say that those two BAPs, if I solve them separately, they don't have anything to do with each other. So I can just solve them separately. But what is this? But we need a concrete idea, a way to express what I mean by this separate problem. So what makes a problem, what makes a BAP separate from another? And this really expands on the idea of a pruned edge set and a critical bottleneck edge. I'm not going to go into too much detail, but we can come up with this idea of a bottleneck cluster, which at the time of writing, the name was a little bit more innocuous than perhaps it is now. But anyways, the bottleneck cluster is a grouping of, in a hand-wavy way, I'd say, it's a grouping of agents and tasks with small allocation costs amongst each other. So it really gives a more concrete way, the full definition of it at least, gives a more concrete way of defining what I mean by a separate BAP. And so using this idea of bottleneck clusters, we can then come up with this question. What conditions do we need in order to treat two BAPs as separate problems? So how far do these cities have to be before you can actually consider them as separate cities, for example? So there are necessary and sufficient conditions for when two bottleneck clusters can be solved as separate problems. And that's all in the second paper that I showed way back at the start, the IFAC paper that I had, way back at the start. Okay, so that's all for the detour. The next thing that I want to talk about is a distributed implementation of this BAP algorithm that we came up with. Okay, so recall the two steps that we needed in our algorithm. The first one was to find and remove the largest edge. And then the second one was to do a distributed search for an MCM, or equivalently, a distributed search for an augmenting path. Now, the distributed removal of a largest edge with a set of distributed agents is actually quite straightforward. It's known as the max consensus problem. So I might have a bit of time to go through it later, but I've left those slides as part of like extra slides if anyone has any questions on how to do that. The more interesting thing that I'm going to talk about today is how to do a distributed search for an augmenting path, the second part. So just a reminder of what an augmenting path is and why we find it so important. This is an augmenting path. We start at a free task and end at a free agent. We alternate between edges in the matching and not in the matching. So we started off with red edges in our matching. And this matching has size 2. And we know that in this 3 agent, 3 task example, we have an MCMs. All MCMs have to have size 3. So we want to recover from this size 2 matching a size 3 matching. And our augmenting path helps us do that, because if we flip the blue and red edges, we regain our size 3 matching. And so it's necessary and sufficient to search for this augmenting path in our algorithm, in our particular case, because it allows us to regain this +1 to our set of edges. Okay, so now let's talk about how to do this distributed search for an augmenting path, where, remember, each agent is assumed to only have access to local information, and it doesn't know this full set of information. So again, we start with a complete bipartite graph. We find our pruned edge set, which, so 8 is the largest of 7, 7, and 8. So 8 is the edge that is our candidate as a critical bottleneck edge. And so we try to remove it and all the edges that are larger than it in our first step. And the next step would be to search for the augmenting path. So given this configuration right now, our pruned edge set, we want to find an augmenting path. And in order to do that, I'm going to use another visual aid down here. So all these agents, they start off by knowing that task B1 is free. And so we make that the root of our search. Task B1 is the root of our search, and we start over here. Now we're looking for an augmenting path. So the first thing we need to do is these agents must decide which of them can pick up task B1. And you can see there are two agents here, A2 and A3, that are able to pick up B1. How do we decide between the two of them which one to search through first? Well, the answer to that is it doesn't actually matter, because remember, this is the pruned edge set. So all these edges are small enough, or are smaller than 8 already. So we know that it doesn't matter which branch we take, as long as we find one that works, we'll find an augmenting path that works for our purposes. So it doesn't matter which branch we take, we can come up with the one that I've just chosen to use for this example is, let's take the minimum, the path that gives us the smallest cost. So agent A3 to B1 has a cost of 5, and agent A2 to B1 has a cost of 6. So let's just go down this path here with a cost of 5. And how do the agents in a distributed way decide that? Well, we know that through a max consensus algorithm, we can find the largest edge. And if we flip that and do a minimum consensus algorithm, so these three agents run a minimum consensus algorithm, they can then say, okay, this agent has the smallest edge, and so we decide to go down this path. Yeah. Again, let's recall like what information we've used so far. We'll notice that it's all just local information, because this agent A2 knows that it was connected to B1, and this agent A3 knows that it was connected to B1. And so we only, at every stage of this, at every point, we've only been using local information and the communication between agents. Okay, so now that we've chosen one path to go down, how do we go from there? Well, agent A3 knows that it's matched to B3, because again, that's local information. So the next point of interest in our search would be B3. So B3 would then be placed up for all agents to see, and all agents would then check, do they have an edge to B3? Again, that would be local information, right? Because agent A2 can check to see if there's an edge to B3, it doesn't. Agent A1 can check if it has an edge to B3, it also doesn't. And so after one round of communication, no one's willing to pick up task B3. So agent A3 will then know, okay, no one's interested in B3, I will give up I will give up B1 and abstain, because I know that I'm a dead end now. And so when we go back to B1, we do another round of checking. We see which agent can pick up task B1. Again, there were two agents, but remember, agent A3 already knows that it is a dead end, so it will just abstain. And so agent A2 will then be the only agent that is viable. And so we go down to agent A2. Again, agent A2 knows that it is matched to task B2. So it knows that it knows this local information, so it can then put up task B2 for all the other agents to see and say who can pick it up. Agent A3 will abstain, so we won't ever go down this path again. And agent A1 becomes the only viable agent that can pick up task B2. And so we go down there, agent A1 picks it up, And when we reach this point, agent A1, using local information, it knows that it's not matched to anything. So it knows that it's a free agent. And so it knows that at this point, we've satisfied all our conditions and we have a success in our search. So what we can, so at this point, agent A1 will just be able to tell all the other agents that we've successfully found an augmenting path. And then we flip the edges, and then we regain our matching of size 3. Okay, so that's how a distributed implementation of the algorithm would work. So the final, how am I doing for time? Okay, so the final thing that I'm going to talk about is just a bit of numerical analysis. So the algorithm that I've come up with, I'm just going to call it prune BAP for the remainder of the slides, just so it's not ambiguous what I'm talking about. So the worst case complexity of prune BAP is just this, where E is the number of edges in our task assignment graph. D is the diameter of the communication graph. I haven't talked too much about the communication graph, but the assumption that I've made for the distributed implementation was just that the agents are able to communicate with each other, and the graph of the communication is modeled as, let me think, it was undirected and connected. Yeah, so the communication graph between agents is just undirected and connected. And also that agents just communicate synchronously. And so D would be the diameter of that communication graph, and the maximum value of that D can take would obviously be N, because in our communication graph with N agents and N tasks, the longest diameter in that the maximum diameter of that communication graph with N agents would have to be N. And N here being the number of tasks or number of agents. The complexity of finding the largest edge, so the maximum consensus algorithm had a complexity of just D, and 2ND comes from the distributed search for an augmenting path. Now, if you want to take one thing away from this slide, it would be just this down here at the bottom. So recall that we, instead of searching for an MCM from scratch, we instead searched for an augmenting path and exploited the knowledge of previous MCMs, of having a previous MCM. So if I scroll back one over here, we had an MCM of size 2. So this is our previous MCM. And instead of searching from scratch for a new MCM in this set, we know that we can just build on this two matching set to a set that contains 3 edges simply by finding this augmenting path. So we make use of this information, and what this allows us to say is the search for an augmenting path only has 2 ND, whereas if we were to try and do it from scratch, it would have a complexity of n to the power of 2.5. And remember, D at most is n, so this has a complexity of n squared, right? So by making use of this information, we're able to avoid the generic MCM finding algorithm and cater our MCM finding algorithm to a particular, to a particular way of finding it. Okay, and this slide over here is, so this slide was supposed to be benchmarking our distributed implementation of solving the bottleneck assignment problem. The problem is that there doesn't actually exist another BAP algorithm, a distributed BAP algorithm. And so there's no real benchmark that we can use to compare this algorithm with. But there does exist other distributed task assignment finding algorithms that aren't catered to the BAP, but do find assignments. So the CBAA is one such algorithm. It is a distributed algorithm, as a distributed assignment finding algorithm, but it's greedy and doesn't guarantee optimality with respect to the BAP, but we can use it just as a comparison to our distributed algorithm. So now, what does this graph tell us? Well, K star is the number of iterations of our algorithm that yields a better assignment than CBAA. So it's the number of times that we have to loop through our removing largest edge, finding augmenting path steps. And so what this graph says is for about a size of problem of about 24 agents, 24 tasks, or 25 agents, 25 tasks, the number of times that we need to loop through that process is only about 2 to 3 times, right? And so, yeah, so that's the last information slide. I'm just going to cap it off with a summary. Today we discussed an algorithm to solve the BAP, and we introduced a distributed approach or distributed implementation of that algorithm. And in particular, what that meant was we needed to introduce a distributed search for an augmenting path. And we also introduced some other structural concepts, the augmenting path, a pruned edge set, a critical bottleneck edge, and also I mentioned a bottleneck cluster. And finally, we talked about what this algorithm allowed us to do as well, as it allows us to warm start rather than start from scratch all the time. Okay. Some other things that we can do with this algorithm and with the BAP is, well, I talked about the augmenting path search, the distributed augmenting path search, and what I showed you was depth first search, because we went all the way down until we reached a dead end. We went all the way back up, and then we tried to go all the way down again until we found a solution. What you could do is, if you're inspired by the breadth first search, you could come up with a different way of searching for this augmenting path that trades off a few. That will trade off between I think complexity with amount of it was the complexity with amount of information that you have to share between agents in each communication round. So you can trade off things by doing different types of searches in a distributed way. The other stuff that you might want to do with the algorithm is try to do more benchmarking with other centralized BAP algorithms, because the way of searching for an augmenting path was unique. So yeah, it's probably worth comparing the complexity of that to other BAP algorithms out there. And the last bit was to do with application-wise. So if we're talking about robots moving to destinations, collision avoidance is actually a property that we can derive out of solving the BAP. And yeah, so thanks for your time. Does anyone have any questions?
Yeah, thanks, Michel. If there is any questions, just send the chat, then we can try to ask it. Oh, okay, Daniel is fancy. He raised his hand. Daniel, do you want to ask your question?
Yeah. Hey, Mitchell.
Hi.
Great talk. I know there's many reasons you might want to do it distributedly, but one of them was privacy, right?
Yes.
So during the search for the augmenting path and doing that iteratively, do the agents end up collecting most of the information about the task anyway over the course of the whole algorithm?
Let me think. So, so the minimum consensus part. So if I go back, let's go back up here. So the augmenting path search, because we've already removed all these larger edges, if you recall, where is it? Yeah, because we've removed all these larger edges, if you remember me saying, it doesn't matter which branch we take at this stage, any branch will do. At this stage, I don't think it's actually necessary to pass any of this cost information around. The example that I gave was to use a minimum consensus, but it's not necessary in this case. The other point where you would share information is all the way back up here, where you want to remove the largest edge. And in this case, you don't actually have to share all of these edges. You only need to share the largest edge amongst each other. So it's not necessarily true in all cases that you will always share all the information in the end. So
Right.
yeah, in terms of that, some information will still be, it's not necessary that all information will be shared all the time.
So there might be like one unlucky task and information ends up being shared with everyone still. Like the very last one you don't.
Yeah, so if you I don't know if this is possible, but if your prune set happened to always only remove one edge at a time, then obviously at every stage you'd be sharing all information with each other because because you're only removing one edge at a time and you're just unlucky. It so happens that every edge is considered. So I believe in cases like those that you would probably end up sharing information anyways. But aside from those cases, yeah, I think not all information will always be shared.
Yeah, cool. So maybe like future work can be, I don't know, information bounds or something like that. But yeah, thanks.
Yeah, but I haven't actually considered like this all in too much detail. So
yeah,
I haven't like considered what's the maximum amount of information that, or the minimum amount of information that would need to be shared. Probably. Yeah.
Great. Thanks, Rachel.
Okay. Thanks. We have another question from another Daniel. Daniel Kevin,
yeah.
Please. Yep.
Thank you. Can you hear me actually?
Yes.
Yes.
Oh, super. Excellent talk. Thank you. I've got a quick question. Have you thought about how to extend this to situations where there are more tasks than agents?
So this,
like more customers than taxis or things like that.
yeah. So this algorithm, even though the examples that I've given so far have been equal number of agents and equal number of tasks, yeah, this algorithm would still work because what we're looking for is an MCM, which is the largest number of edges that we can have in a set that still satisfies this matching property, right? So the algorithm would still work regardless of having an unequal number of agents and tasks. But obviously, if you had more tasks than agents, some tasks would end up not being carried out. But yeah, it would still work for not equal number of.
Okay, thank you.
From an application point of view, Daniel, it's like adding vacuous edges to make it square again. And then when you solve it, those vacuous agents don't matter anymore. So you assign them first, then you continue with the rest. That's from the implementation point of view.
Okay, super.
You can always make the rectangular square. So that's what happens.
Yeah. So they are then agents with no edges.
Yes.
Wait, Imam, that was for That was for like duplicate tasks. So if an agent had more than one.
Yeah, no, but you can do a similar trick here as well. You start adding these imaginary agents that you can start assigning them at the end. Their cost is so low that you never remove those edges.
So
Maybe we can talk about it later.
yeah.
But that's how I
Yeah,
did
yeah,
it.
sure.
Because
That would be very interesting. Yeah.
because like the point I was making is even if as long as the graph is complete, as long as we start off by drawing one edge between every agent and every task, it doesn't matter how many agents and how many tasks we have, as long as we connect all of them together at the start and run this algorithm through it, the solution that we end up with will be an MCM of that graph. Yeah, so it will still be an MCM that we find, and if there were an unequal number of agents and tasks, say 3 agents and 4 tasks, the MCMs of that graph would always be size 3. So we'd always end up with 3 agents to 3 tasks with 1 floating task anyway. So we don't have to add any dummy agents to it. Yeah, dummy tasks.
Okay. Thank you.
So if you don't have any other questions, thank you for your attention. And thanks, Mitchell. It was a very clear talk. Thanks. See you next week for another talk by Tim Strecker next week. Thank you very much.
Yeah.
So let me pause this.